Hello, everyone. Thank you for joining us. We'll get started here in a few minutes. Before we do, I'd like to give you a minute to go ahead and test out your chat function. Let us know where you're tuning in from. I am live from Portland, Oregon. Looks like we've got New Jersey, South Carolina, Toronto, Boston. Hello, hello, hello. Miami, Ohio. It's soggy here too, Ohio. Seattle, our neighbors. Welcome, everyone. Good to see you all tuning in from across the country. Awesome, welcome. And with that, we'll get started. My name is Kara, and I'll be your host as we discuss today's topic, Beyond the Forklift, Unlocking Revenue Critical Workloads on Iceberg, brought to you by StarTree and hosted by VIB. Please take a moment to locate the Q&A button in your window. Use this box to ask questions. We'll do our best to answer all questions, and for those we don't get to, we'll follow up with after. Please feel free to utilize the chat box as we go through today's presentation. And now, without further ado, I'd like to introduce our speakers, Chad and Uday. Take it away, guys.
Great. Thanks, Kara, for that introduction. A little bit about Uday and I are both with StarTree. We're the company behind Apache Pinot. I'm sure some of you are very familiar with Pinot. For those that aren't, you can think of Apache Pinot as a real-time analytic database whose superpower is delivering sub-second queries on very fresh data at massive scale. And at StarTree, we're the commercializer behind that. We offer a cloud managed service version of that, as well as develop enterprise related features on top of that to really drive adoption of Pinot. You can see over now 30% of Fortune 1000 companies are using Apache Pinot in some form or fashion. Companies like Uber, LinkedIn, Walmart, et cetera, are getting value out of it. And a lot of what we're going to talk about today is Apache Pinot vis-a-vis StarTree running on Apache Iceberg and the kinds of problems that solves. But to start, just to get a sense of where everyone in this webinar is at in terms of their journey related to either Apache Iceberg or Delta Lake, curious if everyone could, if we could bring up the poll and interested in where everyone's at. Are you just exploring and learning about open table formats? Are you evaluating options? Maybe you're in the POC phase. Are you in the process of actively migrating to an open table format? Are you already running in production? Or maybe you're in a very mature state and looking to scale Iceberg. All right, so this is super helpful. So like over half of people are in the early stages of Iceberg. That's very normal and typical. And great that you guys could join us today to be that we could be part of that education process. All right, so let's talk a little bit about Iceberg since most of you are sort of researching that and have a good feel for it. Some of the common things that Iceberg solves is one is providing trust at scale. So really what it's doing is it's providing like a database veneer over Parquet files, and that allows you to get consistency and metadata associated with those files. It brings operational simplicity associated with this so that you've got one open canonical table format instead of fragmented data silos. So rather than having, hey, if I want to run Elastic, it's got to be in that table format. If I want to run Snowflake, it has to be in that table format. All of these tools are beginning to now embrace Iceberg so that it can all be in, again, one common shared underlying table format in which you can run a variety of different tools on top of that, which ultimately gives you strategic flexibility, right? You're not locked into a particular vendor because that's where you chose to build your data foundation. And then you can run multiple fit for purpose tools on top of the Iceberg environment. And what we typically see when companies are undergoing a migration to Iceberg is it looks something like this. They build out their data lake, and then they've got ultimately two classes of tools on top of it. One that we'd refer to as procedural processing. So this is around building your data pipelines, maybe deriving new metrics, perhaps even going as far as like creating models, right? And so popular tools here would be things like Flink or Python, things like that, where you're manipulating and processing the data. Then another class of tools that's very common to have on your data lake are what we're referring to as exploratory analytics. So these are SQL engines that allow you to do things like segment customers or do trend analysis. And again, popular tools here would be things like Trino or Databricks or Snowflakes that sits on top of that and allows you to do that kind of, again, exploratory type analysis. Now, the title of this webinar has to do with, beyond the forklift. And everything that I'm describing right here is a forklift, right? If you had a data lake that wasn't on Iceberg and now it is on Iceberg, again, there's really good reasons for migrating your procedural processing and exploratory analytics to Iceberg, but essentially you're delivering the same set of services. And there are other, though, workloads that are certainly data driven that have traditionally sat outside of the traditional data lake and data warehouse. And these have to do with one being like observability or log analytics. Typically, you're either using something like a Datadog or you're putting it in something like Elastic, right? That doesn't lend itself to the traditional sort of data lake format. Or you're building customer or agent facing apps. These are things that require sub-second level SLAs in order to make your app work and perform effectively for the customer. So here, think like, Uber surge pricing. That's taking a lot of data and trying to figure out the optimal price based on supply and demand. You can't wait 8 seconds or minutes, certainly, for an answer to come back. That has to happen super fast. Or interactive analytics or OLAP style, where you've got one question begets another, right? And it's just fast turn. Maybe ultimately you need to ask 50 questions in rapid fire to ultimately diagnose the problem. And again, what all of these have in common and why we're calling it SLA-driven analytics is as a provider of these services back to the organization expects a service level agreement, a commitment that if we're entrusting you to provide us with the data and the tooling to figure out and diagnose an outage and accelerate time to resolution, it needs to happen fast, right? If we're going to deploy a data product in our mobile app, it needs to be sub-second guarantees. And again, for a variety of reasons, these have traditionally sat outside of the data lake. So another polling question before we get on to like how some innovators are really thinking about those workloads on Iceberg. So another polling question for us, how do you currently handle query performance expectations in your data lake? So either you have strict SLAs with monitoring and enforcement, if we could pull the polling question up here. Either you have strict SLAs with monitoring and enforcement, or you have SLAs, but performance is inconsistent, or there's no formal SLAs, but performance is good enough. Performance is a frequent pain point, or maybe you're not sure. All right, the answers are coming in. This one's a little bit more distributed. We'll end the poll and share the results here. So a little bit of a mix, which is interesting. So we got about a quarter of you do have strict SLAs with monitoring and enforcement, and about another quarter of you have SLAs, but performance is inconsistent. And then the other, really the majority, more than half, no formal SLAs, or it is a pain point, or not exactly sure. All right, great. So what we've typically found is because this tends to be a challenge for organizations to be able to guarantee SLAs, particularly on newer open table formats, these workloads tend to sit outside of the data lake and the open table format. Again, because in order to meet those SLAs, the the current crop of tools and technology necessitate a tight coupling of proprietary data formats. This obviously leads to a lot of data duplication. You're either like data is bypassing your data lake in order to satisfy those workloads, or you're replicating data out of the data lake to make another copy in order to satisfy that SLA. And what we're starting to sort of see and certainly advocate in the market is rather than thinking of those things as outside of your data lake, why can't we have workloads running on the data lake that do have performance guarantees on the SLA? And that's where StarTree comes into play. So StarTree would complement existing things like Flink and Spark and Python for procedural processing, or things like Trino, Dremio, what have you, for exploratory analytics. But when you have a high need for sub-second queries or high concurrency demands, that's where StarTree enters the picture. And now I'm going to turn it over to Uday to kind of talk about how that technology works and is able to deliver SLAs.
Thank you. Thank you, Chad. I hope everyone is able to hear me okay. Thank you, everyone, for joining us today on this session here. I'm Uday. I run the R&D team here at StarTree. And I will continue where Chad left off, but I want to kind of step back and introduce how Pinot works and how we are thinking about our Parquet and Iceberg solution, right? So Pinot has traditionally been, and most of the OLAP systems that are out there are traditionally built on strong storage compute coupling, which means that you bring the storage close to the compute so you can produce, really good latencies and really high throughput. With our Iceberg solution, you can call it as a Parquet table or an Iceberg table. We're kind of stepping away from that, right? What we are doing in the Iceberg solution is the Parquet files that are in the storage bucket are not moved into local storage. They remain in the S3 bucket or GCP, wherever your Iceberg table is, but we are able to index them remotely, right? So we pretty much treat the Parquet files as read-only, and then we kind of create indexes on top of them. I'll kind of talk about how that works and why where our key wins are in that model. But when you take a look at query performance, right, depending on where your resource constraints are, there are three key areas when you're talking about the components for query performance that dictate the query performance, right? And especially depending on what the data you're reading and what kind of data you're reading, right? So in case of, let's say, if the data is in local memory that you're querying, your constraints are going to be slightly different than if the data, for example, is in a remote S3 table, right? Suddenly, network latency becomes an issue, throughput becomes an issue, cost to bring the data becomes an issue. So these three components, the time it takes to read the metadata files, prune them, then you have to go scan the files to figure out what data you need to pull in, and then you need to compute the aggregations and serve the responses, right? So there are three key components. Now, depending on what your resource constraints are, each one of these components can play a big or a small role, right? Now, when it comes to Parquet and Iceberg, the data is sitting in an S3 bucket, which is a network hop away, right? So what becomes very, very important is one and two, where you need to make sure that you're pruning the files to avoid reading files that are not required to answer your query, right? So read the metadata to prune files. That's the step one, right? Now, a lot of times, if you take any solution that's out there, ClickHouse, Trino, they do have the ability to read the metadata and prune the files to some extent, right? And we do that too. So that's number one. Now, the second part is once you know that, hey, now my data is in these files, you need to make sure that you are only scanning as little as possible and you're bringing in as little as possible. The reason why that is important is two things. One is, obviously latency, but the second is cost of moving the data, right? And, I'm sure many of us here were surprised with the data transfer costs that cloud providers will bill us. And sometimes it can end up being almost 50% of our entire stack. And I've been bitten by that. So we've taken extra care to make sure that we are being very deliberate in in how much data we are pruning to make sure that we are reading exactly what is needed, right? And the third part is how do you actually move the data, right? So let's say you identified these, this is the amount of data that I need to answer the query. Now, how quickly you can identify that determines how quickly you can respond to the user, right? That's what determines your query performance is. Uh, because it is a long latency operation, if you have to read a megabyte of file, you read it at time 1 versus time 1 plus 10 makes a difference in what is your query latency. It kind of adds to your total query latency, right? So those are the three components. And in the next couple of slides, I will talk about what are the tricks we are using to ensure that we are being as efficient as possible in all three aspects of those, right? So if you look at how Parquet tables or Iceberg tables are set up, you have the Parquet file, and then that is broken into row groups, that is broken into chunks, and it is further broken into pages, right? Now, most other solutions that are out there, they're able to leverage the metadata that Parquet and Iceberg stores, the min-max data, the Bloom filter information to make sure that they are reading the right files, right? So the first thing that happens is time partitioning, right? So you're partitioning the data by time. You're only looking at, hey, I want to look at data for the last 3 days. You're kind of pruning everything beyond those 3 days, right? That's the first level of pruning. Then you have min-max information. Then you have Bloom filter, which allows you to go to the row group and the chunk level, right? That happens in all the systems. We do that too. So that's pretty common. That happens in all the systems, right? Now you identify this is the amount. These are the chunks that I need to read to further filter and further process the data to actually answer the query, right? Now that's where most systems stop. But Pinot is not most systems. StarTree is not most systems, right? A little blag there. What we do is we go further beyond that, right? What we do is because of all of the indexing capabilities we have, we further break it down to the page level, right? So for example, I might have an inverted index. I might have a range index. Range index gives me roaring bitmap of exactly what doc IDs are required for answering a particular query, right? Let's say you say that give me the average of all the transactions between 3:30 a.m. yesterday and 4:30 a.m. Right now, I'm only going to read those pages which match that time range. If I have a range index, if I have an inverted index, on top of that, I'm going to further break it down into docs which match whatever column I'm filtering on. Right, these are all the post filter tasks that happen. Now, when we apply these things, what is going to happen, right? So if you look at the left-hand side, to answer the same query, these systems are pulling around 25 MB of data. Obviously, this is indicative. We have done this experiment with various query sizes, but the ratio proportionality remains the same, right? So these systems are pulling around 25 MB of data, right? Now compare that to Pinot and StarTree, we are pulling around zero point 0.5 MB of data, right? So now there are two aspects here. One is suddenly your data transfer cost has gone down by, I don't know, 5x, 50x, whatever that number is, right? Suddenly you're paying a lot less tax for moving data that is not required, right? You're being very deliberate in what data you're pulling in. But even more important is when we are able to, how quickly we are able to identify this, right? At the plan stage, at post filter stage, we are able to very quickly identify what is required, and we are able to efficiently use the compute. And in the next few slides, I'm going to talk about some of the QPS numbers we've seen, some of the um, uh, query performance numbers we have seen. Chad, can you go back to the previous slide? I'm still working on, I wanted to make another point. I'm sorry. The idea is, let's say you have, 10 pages that you need to process for a given query, right? Now, if you can prefetch those 10 pages such that by the time you're done with the first page, the second page is already available in memory. That also makes it a lot more efficient for you in terms of your compute usage, right? Like I said, when you're talking about Parquet tables, when you're talking about Iceberg tables, you are dealing with a network hop. And one of the things we have done, and this is something, this is not magic. We've implemented these techniques in tiered storage that we launched around 3 years ago. And we've beaten that data path over the last 3 years with extremely large customers, large footprint, and all of our Iceberg solution is built on top of that. So we kind of are sitting on the shoulders of whatever we've built for tiered storage. So that prefetching is really coming to play here. So what happens is, let's say to answer one query, you need 6 pages, right? By the time you're done processing, and we'll issue those 6-page prefetches at the time of post filter stage itself, which means by the time you're done processing the first page, the second page is already available in memory. By the time you're done with this, the third page is there, and so on and so forth, right? So there is no IO wait time. At least we've taken particular trouble to make sure that you're minimizing your IO weights on your CPU, so you're using your compute resources a lot more efficiently, right? And Pinot from the beginning is built on high QPS, and what Chad was talking about, being able to build SLA-driven applications, that means that you're getting machine queries. That means that you should be able to run higher throughput queries, and this is one of the things that allows us to do that, which is being able to do pruning of the data and being able to prefetch the data so that you're minimizing your IO wait time. Right. Go to the next slide, Chad. Now, how are we pruning the data? How are we getting to the exact pages that are required? How are we making sure that we are not bringing any data that is not required, right? Since I joined this company, since I've learned about Pinot around 6 years ago, I've always considered Pinot to be kind of a lazy superhero, right? And this is what I mean. Most systems, most distributed systems are trying to parallelize the work done to come to a response, right? You ask a question about, hey, give me all the users that logged in the last 10, average age of users that logged in the last 30 days, right? You try to split it into 30 days and give it to 30 servers and pull the data and respond in the time it takes to process 1 day of data, right? Now you have distributed the work, get it done as fast as possible. Well, Pinot takes a different approach, and it was more from the need of what Pinot was built for, to be able to ingest extremely high amount of data from Kafka and be able to support hundreds of thousands of QPS, right? Today, for example, we have StarTree clusters that are consuming 100 plus million events per second in ingestion and supporting hundreds of thousands of QPS, right, in query throughput, right? And it's not magic. We still have to deal with physics. And the way we do that is by using all of these different indexes, right? What indexes allow StarTree to do is circumvent the work that is required, right? So if you look at inverted index, I mean, most systems will have inverted index, will have some kind of a sorted index, or a text range index. These indexes are there in other systems, but we kind of give you all of them in a really flexible manner. Now, what these indexes allow you to do is to identify exactly what data is required, and more importantly, identify exactly what data is not required. And this becomes even more important, owing to my previous point, is because the movement of data is a lot more expensive when you're going over a network hop. Expensive in terms of time, expensive in terms of cost that you have to pay to the cloud provider. Now, one of the key indexes that is, even more powerful and that we are seeing a lot of mileage from is the StarTree index, right? The StarTree index, again, I will not do a full justification to StarTree index. That itself is a separate webinar. But the idea is with the StarTree index is we are able to do pre-aggregations in a very efficient manner, right? So most of our analytics queries are doing group by, aggregation, sum, average, things like that, right? Now, what StarTree index at a very, very high level, if I had 5 seconds to explain StarTree index, what StarTree index allows you to do is to create those pre-aggregations but selectively, right? If I do the pre-aggregations for everything, I'm back 10 years ago running Cognos with data mart and things like that, right? That's not what we're talking about. What we're talking about is when you have a column and there are some high cardinality columns, low cardinality columns. Now, when you have a column where certain values have high cardinality, those you pre-compute, but lower than a certain cardinality, you don't pre-compute. Right? Pre-compute obviously as a storage overhead. What StarTree index does is it allows you to toggle that between high cardinality where pre-computing makes sense, do the pre-computing, lower cardinality where pre-computing doesn't make sense, do the computation in line for all of your aggregations. Now that's what StarTree index does. Bloom filter. JSON index is another thing that we are getting a lot of mileage from, especially with some of our current Iceberg users, which who have clickstream data, who have hotel data, where you have JSON blobs that need to be searched through and aggregated. Our JSON index, and I think we have something called as a composite JSON index, which is something that is a StarTree special. Those are the ones that we are seeing even more mileage from, because again the trick is to figure out exactly what data you need and not bring anything that you do not need, right? So Chad, can you go to the next slide?
Yeah, and one other thing, just to plug, one of our colleagues is going to be at Iceberg Summit next week talking about the Lucene index running on Iceberg. So if you're watching this live, you're going to Iceberg Summit next week, try to catch that or catch it on as it streams. And if you're watching this in replay, that'll also be available on replay about the Lucene index on Iceberg.
Perfect. Yeah, thank you. Now, what does this all getting us, right? Hey, I talked about the indexes, I talked about prefetching, I talked about data pipelining, I talked about metadata pruning. What is this all buying for us, right? Well, so far, in the benchmarks that we have done, in the POCs that we have done, in the customers that we've kind of won over, we are seeing incredible results from our Iceberg table, right? And Parquet table, right? 10 to 100x better performance, and the performance comes in terms of query performance, query latency, in terms of throughput, how many queries are you able to run, uh, given the amount of cache that you can allocate. And we have, again, I strongly encourage everyone to take a look at our blog, which goes into quite a bit of detail on what kind of caching strategies we are using to further improve the performance. But the big item that is really winning over for us is the cost, right? Pinot, when we started the company, 6 years ago, the ethos is always to reduce dollar per query, right? To make queries, cheap enough that insights can be driven to everyone, not just the executives, right? That's kind of the, vision of the company for the longest time. And we continue on that drive, right? One of the biggest things that you will see with our Parquet table is your dollar per query. Your serving cost goes drastically down because of the efficiency we bring in, because of the data transfer cost reduction that we bring in, and how efficiently we are using the compute resources that are allocated to us, right? So, and again, I'll share some benchmarks. I probably will not be able to cover and go into full detail on the benchmarks. I really encourage everyone to look at the blog post, which has a lot more detail, right? Chad, go to the next slide. Now, so far, I've talked about being able to pull data in and being able to respond to your queries in a very efficient manner, right? Now, that's for the data that's already in Iceberg. Now, most of our customers already have data in Iceberg, but almost every one of our customers has some kind of a streaming platform. We are a real-time analytics database. Most of our use cases are around freshness of data. And with our Parquet solution, we are not necessarily moving away from that. We are still champions in terms of freshness of data, how quickly we are able to deliver the insights to our end users, right? So from the time someone orders, something on DoorDash or any food delivery company in the world, pretty much, from the time someone places, a transaction on any of your, betting platforms, any of these things, right? all of these rely on the freshness capabilities that StarTree and Pinot bring to the table, right? Now, with respect to Iceberg, we are actually seeing a different paradigm in how people think about data freshness, right? So there is a Kafka stream, but almost all of our users and customers also have a separate pipeline that is taking the data and landing it into Iceberg for long-term analysis, historical analysis kind of a thing, right? Now, this, as it happens, fits quite nicely with our tiered storage model. This is something that we've had for the longest time. It's been there for like 3.5 or 4 years ago. I think that's when we launched it, where we are able to consume data from a Kafka stream, and we are, I can safely say, best at in terms of integration with Kafka and efficiency with which we can consume from Kafka, right? We've kind of proven that beyond any kind of doubt there, right? So now we have a model where you can consume data from your Kafka stream and serve that with all the freshness that you could want, right? But after a certain period of time, when the data becomes older, you are then able to tier it into a Parquet table, right? Now, you can do it in two different ways. You can do offline ingestion for older data and consume only the latest data and retain the latest data in local, or something that we are working on is to be able to take the data only from Kafka and write it into Iceberg, right, into a Parquet table, right? Now, what does it bring to the table? Well, two things. One is, if we are able to write the data to Parquet table, we are avoiding an entire set of pipelines and ETL jobs that you run to write the data into Parquet. But also, when we do write the data into Parquet, you do not have to worry about some of the challenges that we've seen with our customers. One big thing that we've seen is, because even though the data is landing in Parquet, because of the pipelines and because how the data is generated and because how the applications are expecting the data, um, customers end up with lots of small files, right? And they have to go and run another merge job, another compaction job to merge those files, sometimes repartition them. But essentially, there's a bunch of ETL compute cost that is spent to do some cleanup on those Parquet files that are landing from their transaction system or streaming system, right? Now, when we do the write, we've already served the freshness part of it, so we can take the time to create sorted, merged, well-partitioned Parquet files that can be used by your downstream systems. Now, that doesn't mean we won't use it. We've always had the Lambda architecture where you can have real-time and offline in a single logical table. We still allow you to serve the data. So, yeah, as the chart there shows, less than 24 hours, the data will be served from local. More than 24 hours, data can be served from your remote Parquet table. As far as your application is concerned, it will see a single table, right? It will see, let's say, a table which has 13 months of data, and depending on your query, it will either federate the query from the local Pinot servers or use the Parquet table, or if required, merge the two and serve you the results, right? So all of those capabilities are part of our tiered storage, and the Iceberg table that we built just sits on top of a tiered storage solution, so it kind of works nicely there, right? Go to the next slide, Chad. So now, over the last 6 months, we've done a bunch of POCs, we've done a bunch of benchmarking. Again, a lot of this information is in the blog site, and I strongly encourage, if you are thinking about Parquet, if you're thinking about running mission critical applications on Parquet files or Iceberg tables, I strongly encourage you to go review the blog or ping us, and we can give you a lot more details on how the data schema is, how the data sets, what kind of queries you're using. But every good engineer, we try to be objective. We try to level the playing field and make sure that we are doing a as objective and as apples to apples comparison when we are comparing different systems. So we kind of normalized on the query pattern, normalized on the data, normalized on the infrastructure that is used, normalized on the workload generators and all of that good stuff, right? So we've done all of that, and then we looked at, how do we compare, what is our performance, and how do we compare with some of the other open source systems that are out there. Go to the next slide, Chad. This is kind of a self-introspection, kind of a data point where we said that Pinot is obviously best at latency when it comes to OLAP queries and aggregations and group by type of queries. Now, how does our Iceberg table compare to what Pinot brings to the table, right? Obviously, Pinot is faster because again, everything is in a local disk, and I think we are using NVMe systems for this, so there's no surprises there. But where we were pleasantly surprised, and we kind of dug into it and beat it down a little bit more, is our indexing and caching strategy, right? With our Parquet tables, we have two types of caches that customers can take advantage of. And one of the things that has happened in the cloud infrastructure over the last few years, cloud providers are increasingly making it attractive to use NVMe storage. It has become cheaper, dollar to dollar. It's become a lot more cheaper than EBS storage. I think everyone realizes that. And most of these Graviton or these NVMe instances come with a certain amount of storage, right? Now, what we did with our Parquet tables or Iceberg tables is we are using that disk that is allocated to these instances as caches, right? You can size it, you can use all of it or you can use half of it depending on what works for your specific workload. But there are two types of caches that you can enable. On top of the file system cache that is in memory that we all know about, we have disk caches, and one is the data cache or the page cache. That is data that is brought uh, into for any computation, and then there is an index cache. Like I mentioned, we have a lot of different indexes, and you are able to pin those indexes. What it means to pin an index is we don't have to go through the S3 bucket to actually read the index. That's what pinning the index does. Now, pinning the index traditionally meant that you had all or nothing, right? You pin all of the inverted index or you pin nothing. With our index cache, you can essentially pin, you have a cache for your indexes. So only those indexes that are most frequently used or most recently used are in local storage. Everything else is in remote storage, right? Now, the idea is when we talk to Iceberg customers, we are dealing with petabytes of data. So even 5% allocation to local storage becomes very expensive. So we are being very deliberate in our caching strategy. We have most recently used, least recently used, and I think there is a time-based one, which is, keep only the data for the last, 10 minutes or 15 minutes, right? So if you look at this table here, as you're adding caching, you're getting pretty much same as local performance. As you remove cache, your performance kind of, degrades. But the key message is even when you don't have any cache, you're still pretty high, pretty low in terms of, we are talking about 1.5 seconds for most queries, most prominent, OLAP queries, right? So that's kind of what we are able to bring to the table. And a lot of it is because of the indexing techniques and the prefetching and all of that I've talked about, right? The way we run this is we run the query multiple times to make sure that your prefetching can be leveraged in the system. Go to the next slide. Sure. I hope we are doing okay on time.
I'd say another 5 minutes.
Okay, perfect. Throughput, because of all of the prefetching that I've talked about, the fact that we're able to reduce the IO latency, we are seeing a lot higher throughput than you would expect when you're reading from an S3 bucket. When you're serving data from an S3 bucket, you're able to see here filter queries, high selectivity queries. We are able to reach almost the same throughput as Pinot local, even with just the index cache only. You're not caching any data. If you look at that yellow bar there, you're not caching any data. You just have the inverted index in the cache, and you're able to serve 600, 700 QPS for some of those high selectivity filter queries, right? Now, when you go to aggregation queries with map columns, which is kind of your most complex data type that you use in Iceberg, if you have a cache on the system, you are still able to meet as if the data is in local storage, right? So this is another thing. Again, I encourage you to go to the blog. It has a lot more detail, a lot more color on why we are able to accomplish this. And it's to do with the amount of data that we are transferring, amount of prefetching we are doing, and all of those good stuff. Go to the next slide, Chad. This is where kind of rubber meets the road. In this experiment, we are comparing Trino and the iceberg table that Trino provides with StarTree. And again, benchmarking is not easy. I've pushed my team to talk to Pinot expert, Trino experts, talk to people who are practitioners here to make sure that we are not missing any tricks when we are running Trino. So we made sure that everything that is known, that is documented, we are using all the tricks. We've normalized on the hardware. Amount of compute resources is the same. Amount of data or disk storage that is allocated is the same. Partitioning the data, the caches are enabled. I made sure that we are discussing this with Trino experts to make sure that we are not missing any tricks here. Now, the results are clear, right? When you compare Pinot with iceberg table or StarTree's, iceberg table with Trino, the results are startling, right? We are able to serve requests in under 1 second, serve queries in under 1 second, and these are not small simple queries, right? I'm not talking about a simple give me one data point with a filter, right? I'm asking for aggregation. I'm doing count star. I'm doing group bys. I'm doing order bys. And I'm also processing complex data types like map with a filter on a key and an aggregation on a value, right? So these are complex queries that we have seen as we work with our customers. These are samples that we've taken from POCs that we have done, or sometimes, customers have been graceful enough to share query patterns with us, and we are able to see, humongous improvement in, query performance, right? Again, it's not magic. We're still using indexes to reduce the amount of data that we are pulling. We are able to we are able to identify which pages are required so that we can pipeline the data that is flowing from the S3 bucket into the compute engine, into the servers where they're doing the aggregations, right? Go to the next slide. This one compares ClickHouse. Again, same hardware. We've enabled the caches. We've enabled the V3 reader for ClickHouse. We're using the same S3 cluster. The data is partitioned. I'm going to say the data is also sorted, which is something that ClickHouse likes. So we've done that also. Again, the idea was to make sure we are not missing any tricks in using these systems that we are comparing against. We've used all the things that are available in open source, all the tricks that open source systems have. And when we compare again, the latency difference is remarkable, right? Especially when you have more complex queries, it becomes even more predominant in terms of what we are able to serve, how we are able to serve the request, right? So here you are seeing 15 seconds to 1 second kind of a difference, right? Less than a second kind of latencies for aggregation and group by, right? Again, uh, not magic. We are using StarTree index. We are using inverted index. All the indexes that are at our disposal, we are using all of those to make sure that we are being as efficient as we can, right? Uh, I think there is a lot more data, again, a lot more detail. One experiment I've asked the team to run recently that we have seen is when we look at the network bandwidth, right? When we run these experiments, one of the things we keep an eye on is how much data is being transferred. And we validated that over repeated experiments. We run around 1/5 of the data gets pulled in for any of these queries across the board. On average, 1/5 is the amount of data that we are reading in terms of number of gets and the amount of data that we pull, right? Now, that's a big cost savings. That's a big cost component when it comes to iceberg tables. right? That's a big cost savings, and that is something that we are able to do. And that is also part of the throughput that we are able to generate with, with these benchmarks, right? Do you have one more slide? I think that's the last slide.
Yeah,
Yeah.
that's a wrap on it. But we did have some questions come through. And I think the first one, you're probably best qualified, Uday, to answer. It was what kind of overhead is there when adding an index on
Yeah.
Iceberg?
Yeah, so the when you point us to an iceberg table, what happens is we have minion framework where these minions are background tasks that spin up and spin down, and these jobs get started and they start ingesting the data, not well indexing the data. Sorry, force of habit. Now the data is available for query before the index is created. Creating the index is an offline operation that doesn't predicate whether you can query the data or not. You can query the data a lot faster, within seconds of you pointing us to the Parquet table. The indexing is an offline operation, and the minions will come in, they will create the indexes in an offline process, and they will spin down, right? That's a completely separate process. We do not use the iceberg table or the bucket where the iceberg files are. We do not write anything to that. We write to a separate, S3 bucket or GCP bucket, depending on the cloud provider. But it's an offline operation. It doesn't predicate the freshness of the data.
All right, excellent. I had a question come in. Looks like this person is already a Pinot user. Thank you. And they also have an active Iceberg migration as well. And essentially the question is like, where can he go for more information around what we're talking about, around how to make the two work together?
Yeah, I think the blog is the first place where you want to start. We have detailed, and there is one more that is coming up. Arun is going to publish another blog. Arun or Chinmay, we'll have another blog that we will publish with a lot more detail on how to set it up, how to get it running, and all of that. And reach out to any one of us. Reach out to StarTree. I'm sure there you go. The QR code will get you a demo, and Chad will join, and kind of sell you iceberg table.
No, that's right. You can go to our website too and request to talk to an expert, and we can talk through what you're looking to do and some of those challenges. All right. Well, that concludes the formal presentation and the Q&As. Want to again thank everyone for joining us today. Fantastic turnout here. We'll be sending out the replay link to everyone here too, if there are any things you want to go back and check out or share with some colleagues. So again, thank you for joining.
Thanks, everyone.
All right. And with that, we'll go ahead and close out. Thank you everyone for attending our webinar today. We hope you enjoyed it as much as we did. If you registered through VIB with your business email and have any questions, please contact webinars@vib.tech. Thank you again and have a great day, everyone.
Thank you.
Thanks.